For an example of Snell's law, let's do number 43 out of chapter 32. Here we have a light beam strikes a 2 centimeter thick piece of plastic with a refractive index of 1.62, so this is 2 centimeters, at a 45-degree angle. The plastic is on top of a 3 centimeter thick piece of glass, 3 centimeters, with a refractive index of n, which is 1.47, and we want to calculate the distance from where the light enters to where the light exits. So we can write Snell's law. We can say that the in air times the sine of theta air is equal to in plastic times the sine of theta plastic. And what we want to find is theta plastic, so theta plastic is equal to the arc sine of in air sine of theta air over in plastic. So that's equal to air is just 1. It's a little over 1, but we'll just use 1. My theta air is 45 degrees over my refractive index of the plastic is 1.62. And that gives me 25.88 degrees. Now I want to find this distance here. We'll call this D1. And D1 is just going to be equal to the distance of the plastic times the tangent of theta plastic. And the reason why we have the tangent is D1 is the opposite side, D plastic is the adjacent, and that opposite over adjacent is equal to the tangent, and so I'm just rearranging that equation. So that gives me 2 centimeters times the tangent of 25.88 degrees, and that's equal to about 0.97 centimeters. Now I can work on my angle here for the refractive index inside of the second medium, and that's going to be in plastic times sine of theta plastic is equal to in glass times sine of theta glass. And I'm interested in theta glass. So theta glass is equal to the arc sine of in plastic times sine of theta plastic divided by the in glass. So the refractive index of the plastic is 1.62. Sine of 25.88 degrees divided by, oh, and I forgot my arc sine there, okay, and divide that by our in glass, and that's 1.47. And that gives us 28.752 degrees. Now, that's at this point here. You can draw a vertical, and this distance of the vertical is just 3 centimeters. So now I have distance 2, which is this horizontal distance, is equal to the distance of the glass times the tangent of theta glass, and that equals 3 centimeters times the tangent of 28.752 degrees, and that gives me 1.646 centimeters. So my total distance is equal to d1 plus d2. That's 0.97 centimeters plus 1.646 centimeters, and that gives me a grand total of 2.616 centimeters. Now we can look at the exiting angle here just for the fun of it, and that's going to be in air times sine of theta air, and that's this angle down here at the bottom, is equal to in glass times sine of theta glass, and I'm looking for theta air, and that's equal to the arc sine. In air is just equal to 1, so I'm going to have the arc sine of in glass times sine of theta glass, and that's just the arc sine of 1.47 sine of 28.752 degrees, and that comes out to be 45 degrees. So when you have parallel interfaces, then the entering ray is going to be the same angle as the exiting ray. So the exiting ray will always be parallel to what's entering into the object or the layers. This only works if everything's parallel to the surface.